This week we will be completing the competitive nucleophiles lab, which can be found on page 47 of your lab manual. In this week's lab, we will be comparing the relative nucleophilicity of two halide ions, a chloride and a bromide ion, with two different alcohols, 1-butanol and 2-methyl-2-butanol. Before we talk more about the lab, we'll first talk about nucleophilic substitution. Shown here is a general reaction for a nucleophilic substitution reaction, in which on the left we have our nucleophilic reagent. The nucleophile is typically a metal salt such as lithium bromide or sodium hydroxide that reacts with an electrophile. This must contain a carbon leaving group bond which is polarized towards the leaving group. In this case, our leaving group is this halide here. So this reacts. The electrons from the nucleophile attack the electrophilic carbon, and that displaces this halide ion, giving us our products of the reaction. Nucleophilic substitution reactions can be broken into two different kinds. The first one I'll talk about is an SN2 reaction. So S stands for substitution, N stands for nucleophilic, and the 2 stands for bimolecular. So this is a bimolecular reaction. The rate law for this reaction depends upon the concentration of both reactants. So here's the rate law down here. So it depends upon the concentration of the substrate and the concentration of the nucleophile. And both reactants are involved in the rate determining transition state. That's why this is a bimolecular reaction. And what happens is you get nucleophilic attack from the nucleophile on the electrophilic carbon. This leads to a 5-membered transition state where you simultaneously make that carbon nucleophile bond and then break that leaving group carbon bond to get our products. Shown here is the reaction coordinate diagram for an SN2 reaction. So shown here is the nucleophilic attack on the electrophilic carbon by our nucleophile, which is a hydroxide ion, that leads to this 5-membered transition state, which is higher in energy. And then our products are shown here, the alcohol and then the bromide ion, which is displaced, and those are lower in energy. Strong nucleophiles favor SN2 reactions. So what is nucleophilicity? Well, it can also be thought of as nucleophilic strength, and it's a measure of how fast a nucleophile reacts with a substrate to displace the substrate's leaving group. In this case, we have a reaction shown here, a substitution reaction in which dimethyl sulfide is our nucleophile and iodomethane is our substrate. That nucleophile displaces our leaving group in this case, which is an iodide anion. Nucleophilicity increases across the periodic table from right to left, so this tracks with basicity. However, going down the periodic table, nucleophilicity increases, and this does not track with basicity. You can think of it as larger anions are more polarizable, and thus they're more nucleophilic. You can also think of this in terms of solvation. So solvation also plays a role in that smaller anions are more easily solvated and shielded from acting as nucleophiles, whereas larger anions are more difficult to solvate, and thus they are more available to act as nucleophiles. Now, if we think of solvent effects in SN2 reactions, polar aprotic solvents are good for SN2 reactions. Polar solvents are good because they solubilize our nucleophile, and protic solvents would form strong hydrogen bonds with the anionic nucleophiles, decreasing their reactivity. So in the other case, looking at polar aprotic solvents, this still solubilizes our nucleophile, however it does not form those strong hydrogen bonds with our nucleophile, and thus the exposed nucleophile in a polar aprotic solvent reacts rapidly in an SN2 reaction. Now if we think of steric effects in an SN2 reaction, if we decrease the size of the constituents on the electrophilic carbon atom, we will increase the rate of substitution by the SN2 mechanism. And if we think about the mechanism, we are attacking the side of the carbon opposite of the leaving group, so smaller substituents on that carbon allow the nucleophile to more readily attack that carbon atom. Thus, the methyl halide, or whatever the leaving group is, will be the most reactive in an SN2 reaction. The other kind of nucleophilic substitution reaction is an SN1 reaction. So again, S stands for substitution, N stands for nucleophilic, and the 1 means that this is a unimolecular reaction. So in this reaction, first a leaving group leaves, then we get this carbocation intermediate, where our nucleophile in this case can either attack from the front face here, or it can go around and attack the back face here. And this gives us a racemic mixture of products. In some cases, this can be a 50-50 mixture of both stereoisomers. However, the amounts of both can vary depending upon the reaction. This is a unimolecular reaction because the rate law depends upon the concentration of the electrophile. So it's showing here is the rate equation. And only the electrophile is involved in the rate determining transition state for this reaction. Shown here is the reaction coordinate diagram for an SN1 reaction. First thing that happens is our leaving group leaves. This gives us our carbocation intermediate, which then the nucleophile, being water in this case, attacks that carbocation, giving us this charged species here, which then another molecule of water can then deprotonate this species to give us our end products, which is this alcohol, bromide ion, and then hydronium ion. Now thinking about rates of reactions in SN1 reactions, we need to think about the mechanism of this reaction that's shown at the bottom. So first what happens is our leaving group leaves, and this gives us our carbocation intermediate. This is the rate determining step of this reaction. So if we stabilize this carbocation intermediate, we can increase the rate of the reaction. And thus, the electrophilic carbons, which are tertiary carbons, react faster, as alkyl groups in this case will stabilize our carbocation intermediate. Now if we think of solvent effects in an SN1 reaction, polar protic solvents are good for SN1 reactions. And this is because their polar nature stabilizes the transition state and decreases activation energy required for the reaction to occur. And their protic nature stabilizes the transition state due to hydrogen bonding with the negatively charged leaving group. To compare SN1 and SN2 reactions, to compare the substrate, in an SN1 reaction, the reactive carbon is usually a tertiary carbon, and again we can think of this as stabilization of our carbocation intermediate. Whereas in an SN2 reaction, or our substrate, the reactive carbon is usually a primary carbon or even a methyl carbon, and this is due to decreased steric effects. The nucleophile for an SN1 reaction is usually weak to medium strength, whereas in an SN2 reaction, the nucleophile is usually strong, usually a charged species. The solvent in an SN1 reaction is usually a polar protic solvent, whereas in SN2, it's usually polar aprotic. Thinking about stereochemistry of an SN1 reaction, again, since we're generating that carbocation intermediate, we'll have a racemic mixture of products, whereas in an SN2 reaction, we're not generating that carbocation intermediate, and thus we're getting 100% inversion of our stereocenter. Now for a summarized procedure of this week's experiment. Before we talk about the experiment, we will briefly go over some safety considerations for this week's lab. The first is that we will be working with sulfuric acid, so this is a strong acid, and this is corrosive and can cause skin burns. So if this is spilled, please tell your TA. They can neutralize it with a weak base, and then they can clean up the neutralized spill with water and paper towels. If it's spilled on your skin, immediately alert the TA and wash your skin thoroughly with water for at least 15 minutes. Make sure to always wear gloves and goggles in the laboratory, and at the end of the lab, dispose of your liquids in the liquid laced jug and your solids in the bucket. Again, the purpose of this lab is to compare the relative nucleophilicity of two halide ions, being chloride and bromide, with two different alcohols, being 1-butanol and 2-methyl-2-butanol. So what we'll be doing is we'll be adding an acid, dilute sulfuric acid. This protonates the alcohol, making this a better leaving group, and then this can be displaced by a nucleophilic substitution reaction with our nucleophiles. First, we'll be preparing the solvent nucleophile medium. So first we'll combine 4.75 grams of ammonium chloride and 8.75 grams of ammonium bromide in a 250 milliliter Erlenmeyer flask. Then with caution, add 44 milliliters of 7.7 molar sulfuric acid to the ammonium salts, a little at a time. Then swirl the mixture to dissolve the salts, and if necessary, heat the mixture. Allow the mixture to cool and add 17 milliliters to a separatory funnel, and then add the remainder to a 100 milliliter round bottom flask with a reflux condenser. Then you can start your reaction with 1-butanol, and this will be in the reflux apparatus. So first add a boiling stone to the reflux apparatus, and then heat the reaction at a gentle reflux with the reflux ring less than a quarter of the way up the condenser. And this is because violent boiling will cause loss of product. Then heat the reaction for 75 minutes. While this is reacting, you can then move on to the 2-methyl-2-butanol reaction. For the reaction with 2-methyl-2-butanol, which is in our separatory funnel, we will add 2.5 milliliters of 2-methyl-2-butanol to the separatory funnel. We'll then roll and vent this reaction until pressure is equalized. Then we'll shake the funnel fairly vigorously while venting while we're doing this. Then we will allow the mixture to separate, and we'll drain the bottom aqueous layer. We'll then drain the organic layer into a different flask that contains sodium bicarbonate, and then we will decant our liquid from our solid that's left over in the flask. Now finishing up that reaction that is under reflux, so the 1-butanol reaction. After the 75-minute reflux is done, we will then let cool in an ice bath. We'll then transfer that reaction to a different separatory funnel. We'll drain the aqueous layer, wash the organic layer with saturated sodium bicarbonate solution, separate those layers, and then dry the organic layer with anhydrous sodium sulfate, and then we'll decant the liquid from the leftover sodium sulfate into a new flask. Once both reactions are done, we will be analyzing our product mixtures by refractometry. These are the refractometers that are in our labs. We will measure the refractive index of both of our product mixtures. The refractive index takes advantage of the fact that light travels at different speeds in different mediums. This will allow us to calculate the percentage of alkyl chloride and alkyl bromide in our product mixtures. we will use the refractive index of the alkyl bromide minus the refractive index of our product divided by the refractive index of the alkyl bromide minus the refractive index of our alkyl chloride times 100% to give us the percent of alkyl chloride in our solution, and then by simple subtraction we can figure out the amount of alkyl bromide in our mixture.